9.2.1 Infinite Geometric Series. Review of sequences. A geometric sequence is a sequence in which each term is equal to the previous term multiplied by a constant. So, when we look at the recursive formula of a geometric sequence, we have that the value of our term un is equal to the constant ratio multiplied by the value of the term un minus 1. Here the explicit formula, when we're looking for un, if we have the value of un will equal u1 multiplied by our constant ratio raised to the n minus 1 power. Now, if we don't have un and instead they give us u0, un would equal u0 multiplied by that constant ratio raised to the nth power. Here's an example. In this example, Jack baked a pie and promptly ate 1/2 of it. Determined to make the pie last, he then decided to eat only 1/2 of the pie that remained each day. So, first of all, we're looking to record the amount of pie eaten each day for the first 7 days by Jack. Oh, on the first day, he ate 1/2 of a pie. On the second day, he ate 1/2 of a half of a pie. That's 1/4 of a pie. On the third day, he ate 1/2 of 1/2 of 1/2 of a pie, or 1/2 of 1/4 of a pie, which is 1/8 of a pie. So, on the fourth day, then, he ate 1/16 of that pie. On the fifth day, he ate 1/32 of the pie. Sixth day, he ate 1/64, and on the seventh day, he ate 1/128 of that pie. He starts by eating half of it, but then he's eating very little of it. So now let's look at part B. For each of the 7 days, record the total amount of pie eaten since it was baked. Well, on the first day, he ate half of the pie, so he only ate half of the pie. On the second day, well, he ate on the first day half the pie, and then on the second day he ate 1/4 of the pie. So 1/2 plus 1/4, already he ate 3/4 of that pie. Which means on the third day, he ate 1/8, but on the second day he ate 1/4, and on the first day he ate 1/2. So add all those together, and he's already eaten 7/8 of the pie by the third day. On the fourth day, then, he'll have eaten 15/16. On the fifth day, 31/32. On the sixth day, 63/64. And finally, on the seventh day, he'll have eaten 127/128. So, I'd say by the seventh day, he's eaten majority of the pie. Part C, though, asks us if Jack here is living forever, and the pie obviously never expires, then how much of this pie will he eat? Well, he's eating 1/2 a pie a day forever. And already by day 7, he's almost eaten the whole pie. So, here, we'd say he eats about 1 pie. As we can clearly see, this will go on forever, eating 1/2 of the pie a day, 1/2 of the pie a day, and 1/2 of that half, and that, and 1/2 of that half. So it'll continuously approach eating the whole pie, but he will never quite eat the pie. So we're going to estimate our answer here and write about 1. Now, let's apply this to some new math terminology. The indicated sum of a geometric sequence is a geometric series. What this is saying is stuff we've already done. The sum of a geometric sequence. So we're looking here as 7. That is the sum of the amount of pie he had eaten on the first 7 days in this series, which we found to be he had eaten 127th, 128th of a pie on day 7. Now, looking for an infinite geometric series, that is a geometric series with infinitely many terms. Here, this is that Jack lives forever. There are infinitely many terms when Jack lives forever. So that is actually the question in part C. Finally, a sequence of partial sums that approaches a long-run value as the number of terms increases is called a convergent series. So we would say that Jack eating half a pie a day converges to 1. Thus, this is a convergent series. Now, looking into our book definitions, a convergent infinite geometric series. An infinite geometric series is a convergent series if the absolute value of the common ratio is less than 1. And here it shows us numerically that the absolute value of our common ratio r must be less than 1. The sum of infinitely many terms s of a convergent infinite geometric series is given by the explicit formula s, the sum of this series, equals u1, where u1 is the first term, divided by 1 minus r, where r is the common ratio. And since we're subtracting 1 from r, it makes sense that the absolute value of r must be less than 1. So now let's consider the infinite series. Sum from when n equals 1 to infinity of 0.3 multiplied by 0.1 raised to the n minus 1 power. So to start, let's display the sum as infinitely many terms in a decimal. So first of all, I need to find when n equals 1, what does my first term of the series equal? So when n equals 1, plug in 1 wherever I have n in the series. That's just in that exponent there. So 0.3 times 0.1 raised to the 1 minus 1 power. Well, that's the same as 0.3 times 1, which is just 0.3. So my first term in the series would be 0.3. Then I would need to add to that when n equals 2. So 0.3 multiplied by 0.1, well, that equals plus 0.03. Then when n equals 3, well, that term would be 0.003. And when n equals 4, 0.0003, and so on. Actually, in fact, this goes infinitely long. So if I were to add all these terms together, though, I know I'd get 0.3, 3, 3, 3, repeating. So my indefinite sum would be 0.33333. Repeats. Now, let's use what we've learned today. Well, actually, in the past, we could tell us what the first term in this sequence is. So u1, that's just our 0.3. Now, the common ratio, well, when I'm multiplying by everything, is just that 0.1. So our common ratio is 0.1. Let's express the sum as a ratio of integers. Well, I know the sum is equal to the first term divided by 1 minus the ratio. So if I were to plug in u1, that'd be 0.3 divided by 1 minus 0.1. 0.3 over 0.9, which just equals 1/3. And if I were to look back to part A at my answer, I'd see 0.3333 repeating. Well, I know that as a fraction is 1/3. So I would say that the sum of the ratio of my integers is 1/3.